Okay, so welcome everyone. Today's speaker is Thea Mihailescu, and she's a postdoctoral researcher at NASA's Goddard Space Flight Center and USRA, where she's working on spectroscopy and plasma composition using data from Solar Orbiter SPICE and Hinode ICE. She studied Bachelor of Science in Physics at Imperial College London and a Master's of Science in Space Science and Engineering at University College London. And then she finished her PhD in solar physics at University College London's Mullard Space Science Laboratory last year. And her PhD work focused on using spectroscopic data from Hinode ice to characterize plasma composition variations in the sun's corona and understanding the properties of the drivers responsible for these variations. And so today she'll present on the plasma composition variations in solar active regions. Right.
Okay. Thank you very much, everybody, for joining. So yes, I'm a postdoc at NASA Goddard. I mainly work with spectroscopic observations of plasma composition variations in the solar corona with Solar Orbiter SPICE and Hinode ice. But this particular talk, I'm mainly going to talk about my work using Hinode ice data to look at plasma composition variations on large scale and smaller scales in active regions. So just as a quick introduction a general introduction to solar plasma composition, we can measure the plasma composition at various parts in the solar atmosphere, starting from the photosphere. We can do that using white light spectroscopy or helioseismology, and it's found to be constant. So it doesn't vary with time and it doesn't change across the surface. There's no instrumentation that we can currently use to measure the composition of the chromosphere, but when we go into the corona, we can measure it using EUV or X-ray spectroscopy in flares, and it was found that the composition is variable, so it doesn't just change with time, but it also is different in different parts of the corona. And the same variability is seen in situ in solar wind or coronal mass ejections measurements, which raises the question of what is causing this variability, because the plasma in the corona and in the solar wind does come from the photosphere. So something along the way from the photosphere up into the corona must be changing the composition for us to observe these changes in the corona. So this is sort of a relatively broad research topic, but the main bit that I'm focusing on is the EUV spectroscopy part, looking at composition variations in the corona. So when we talk about plasma composition variations in the corona, we mainly refer to the FIP effect. So this is the process whereby elements that have low first ionization potential become enhanced in the corona, compared to elements that have a high first ionization potential that don't. They retain their photospheric abundances. And the sort of separation between low FIP and high FIP is at about 10 electron volts. So below 10 electron volts, those are low FIP elements. Above 10 electron volts, those are high FIP elements. And we can measure the degree of enhancement using the FIP bias parameter. So the FIP bias parameter is essentially the ratio between the coronal abundance of an element over its photospheric abundance of the element. Ideally, we want to measure the abundance. We need a reference for measuring the abundance, and that reference ideally is hydrogen. But because we can't measure the hydrogen abundance in the corona, we need to choose a different reference. So what's typically done is, instead of measuring the abundance of an element relative to hydrogen, we measure it relative to another element that we know has a high first ionization potential. So we don't expect it to have any variations in abundance going from the photosphere to the corona. So a few examples of that are oxygen, argon, and neon. And another example that's usually used is sulfur, but I'll talk about that more later. So typically we measure the abundance of a low FIP element relative to a high FIP element in the corona. We divide that by the photosphere, and then that gives us the FIP bias. And the plot on the top right-hand side is showing sort of schematically this enhancement. The FIP bias is a function of ionization potential for a few elements that are abundant in the sun's atmosphere. So you can see on below about 10 electron volts, we have elements like calcium, silicon, iron that show this enhancement of 2, 3, 4, and even higher sometimes. And above 10 electron volts, we have high FIP elements that don't show enhanced abundances. So in terms of language, if we have a FIP bias equal to 1, we typically call that photospheric composition, because it means that particular part of the corona that we're looking at has the same elemental abundance as the photosphere below. If we have a FIP bias higher than 1, then we call that coronal composition. Typically, we want it to be significantly higher than 1, so something like 2, 3, 4 or higher, because it essentially shows us there's some variation in that part of the corona. So we see photospheric composition in coronal holes on disk and in the fast solar wind in situ, and we see photospheric composition in coronal holes in the fast solar wind and coronal composition in active regions, typically a little bit in the quiet sun as well, and then in the slow solar wind in situ. So a few sort of typical FIP bias diagnostics are silicon to sulfur, calcium to argon. These are common in Hinode ice observations or data analysis. And then we have magnesium to neon, which is typical for solar orbiter spice. And iron to oxygen is a typical one measured in the solar wind, which people use to relate in situ observations to on disk observations. So in the solar corona, this is what a FIP bias map looks like. So on the left-hand side, that's iron 13202 from Hinode ice. So that you can see the different features on the sun's atmosphere at the time. And then the right-hand side shows the FIP bias. So I've highlighted 2 examples there. One of the coronal hole, which has very clear no to low FIP effect, and then an active region that shows very, very strong FIP effect.
Is that the full sun?
The one on the right, yes.
Okay.
Yeah. So this is actually quite a special map, because Hinode ice has a low field of view. So this was constructed by taking 26 Hinode ice scans and then over up 1.5 to 2 days, and then you stitch them all together and you get the full sun map. Yes. In the solar wind, we also observe the FIP effect, and it seems to be correlated with the solar wind temperature and anti-correlated with the solar wind speed. So and the plot on the top right hand side shows that nicely. So in the portions of high speed, so we're looking at the fast solar wind, we see that's in red. And then in the blue, we have temperature, and in the green, the magnesium to oxygen line ratio, which is a proxy for the FIP bias. So in the regions that have a high speed, so we're looking at the fast solar wind, we see low or no FIP effect and lower temperatures. But then if we go to regions that have slower speeds, so we're looking at the slow solar wind, these have much higher FIP bias values and higher temperatures. And this is consistent with the origin. We know the fast and solar wind streams to have. So in the fast solar wind is known to originate from coronal holes, and it shows no FIP effect, and so do coronal holes. And in the slow solar wind, some potential candidates for the origins of the slow solar wind are active region edges and coronal hole boundaries, and they all show increased FIP bias on disk and in the solar wind as well. And and I have an example on the bottom here of sort of how plasma composition signatures can be used to sort of track where a parcel of solar wind measured in situ originates from on the sun. So so the plasma composition doesn't really change from the corona when we go into the solar wind. So we can use that as a signature for finding out where a particular parcel of solar wind came on disk. But then we also have other requirements. So we want an outflow in that part of the corona, so the plasma is moving upwards, and then we also want open field so that the plasma can escape into the solar wind.
Not to interrupt, but I think Phil has a question.
Oh, yeah.
Yeah, thank you. Hi, Claire. This is Bill Judge.
Hello.
I was just wondering if there's a correlation, what the correlation is with density in the solar wind.
I don't know the answer to that question, actually.
Because I think the coupling between the various ions is going to depend much more strongly on the density in the chromosphere than it is with anything like the temperature. So, but as far as I remember, isn't the mass flux about the same in the far solar wind as the slow? And then if that's the case, then the density should be inversely with the solar wind speed. And so there should be some correlation there, but does anybody know?
I have to admit, I don't know.
I think it's about a factor of 2 between them.
Oh, okay.
Roughly, we're talking hand waving here, but yeah.
Okay, so there is a difference as well.
Not a lot, but yeah, roughly factor of 2. Okay. Looking at Kevin Rim.
You don't.
Yeah, so yeah, maybe a factor of 2 then. Yeah.
Thanks.
While we've interrupted, can you go back to the full disk map just?
Yeah,
Sorry. No, yeah.
this one.
So is there, I mean, the fast wind also comes from the poles, right?
Yes.
So you should see some effect. I would expect the poles would show,
Oh, lower FIP effect.
right, the lower FIP effect.
That is a good question.
I squint hard enough. It doesn't seem, I don't know. Yeah.
Yeah. I mean, it definitely I think you'd have to actually look into the values.
Right.
It's not a high FIP bias, but you're right, it might not be exactly 1. So if you compare the coronal hole I pointed to the poles, it does seem like the coronal hole
Higher.
a little, I would have said a little lower than the
A little
poles.
lower, maybe. I don't know what yeah.
Yeah.
But then,
Um,
okay.
Yeah, so maybe you see, I think it probably depends on some of the properties of the coronal hole as well. I'm not entirely sure. I mostly
Right.
look at active
Yeah,
regions.
right.
Yeah, but that's a good point.
Just to just, yeah, see if there's any.
Yeah.
I have a quick question too.
Yes.
So you're looking at it in situ, but you're bringing it back to either coronal hole boundaries and active regions. So you must see a solar cycle effect because the active regions are.
Yes. Just give me 2 more slides. Yeah. Yeah. I can come back to that when I get to that slide. Okay, so this was in the solar wind. Oh yeah, it's here. So we also see this correlation of the FIB bias for the sun as a star. This study was done using measurements from SDO Eve. So the plot on the left is showing how the solar cycle varies, and using the F10.7 index, which is a proxy for solar activity, and you can see nicely solar cycle 23 and 24, I think, are there. And then the plot on the right-hand side, the blue curve is showing the F10.7 emission, and then the red is showing the FIB bias for the sun as a star variation over those 3 years. And we see a very good correlation between the solar activity and the FIB bias. And this is probably because the higher the solar activity, the more active regions we have, and the active regions is where we see the strongest FIB enhancement. So this is probably why we also see a stronger FIB enhancement overall when solar activity is higher. Does this answer your question? Oh, okay. So when thinking about plasma composition variations, we mainly refer to the FIB effect, and this is believed to happen in the chromosphere. So we see no changes at photospheric level. We see some changes at transition region level. So whatever is changing the composition must be happening in the chromosphere somewhere. And the model that seems to best explain it currently is this ponderomotive force model developed by Martin Lamming. So the ponderomotive force model proposes that the FIB effect is driven by the refraction and reflection of coronal alpha waves, that when these coronal alpha waves reach the chromospheric foot points of active region loops, they drive this ponderomotive force on the ionized material in the chromosphere, and then they bring the ionized material in the chromosphere upwards to the transition region level. And this is where the separation between low FIB and high FIB elements comes in, because low FIB elements have a much higher ionization fraction in the chromosphere than high FIB elements. So in the chromosphere, the population of low FIP elements will be mostly ionized, whereas the population of high FIP elements will be ionized to a lower degree. So that means more of the low FIP elements will experience this additional upwards acceleration, and this results in the overabundance we measure at transition region level and into the corona. So there are three main parts to the sort of simulating the fractionation process using the ponderomotive force model. The first one is modeling the chromospheric environment. So based on temperature and density variations as a function of height, using the Saha equation, we can calculate the ionization fractions for all the elements that we're interested in as a function of height. And then that is the first part, the chromospheric environment. And then we propagate a wave through the corona and through this modeled chromospheric environment. And based on the properties of the wave we selected, the reflection and refraction when the wave reaches the chromospheric environment will have different profiles. And this will lead to different ponderomotive force profiles, which will lead to different fractionation patterns, so different enhancement when we get to transition region level. And the third part is just going from the ponderomotive acceleration profile to what enhancement does that translate to at transition region level. And although this is typically the main thing we think of when we talk about plasma composition variations, there are a few, oh, sorry, I had another point on this, which is that, so in the ponderomotive force model, the idea is that the fractionation process happens in the chromosphere, and then plasma with changed abundances is moved along coronal loops up into the corona. So that happens, the fractionation process happens at the foot points. And in observations, we do see enhanced FIB bias at the foot points of active region loops. And I have an example of that on the left-hand side here. So this is the MDI photospheric magnetic field map for an active region, and the right-hand side shows the FIB bias. And you can see that the strongest patches of FIB bias enhancement is associated with regions of strong magnetic field. So we're actually looking at foot points of the coronal loops in this active region. And then we also see slightly more enhanced FIB bias values along the loops connecting these foot points, and those are shown in the dotted lines connecting the circles and ovals. And an important thing is that when we measure the plasma composition variations, we look mainly in the corona, but the ponderomotive force model is simulating the chromospheric environment. So how do we link this chromospheric process to what we see in the corona? The plot I'm showing on the right-hand side is looking into doing this by connecting signatures of alpha wave activity in the corona. Those are shown in the in the chromosphere. Those are shown in the blue dots in the center of this sunspot. And they are magnetically connected to regions of enhanced FIB bias in the corona detected by Hinode ice. So this gives us confidence that the regions we see have a stronger FIB bias enhancement are magnetically connected to these regions in the chromosphere that show higher signatures of alpha wave activity, which supports the idea that what drives the FIB effect is this this process of wave refraction and reflection in the chromosphere driving the ponderomotive force. But on top of having the FIB effect change the plasma composition we observe in the corona, there's other things that we need to take into account as well. The first one is the transport of plasma from the transition region into the corona, because once we reach the transition region level, the ponderomotive force becomes very low, or it disappears completely. But more importantly, everything becomes ionized. So we no longer have this separation between low FIB elements and high FIB elements. So even if there was a ponderomotive force up higher than the transition region level, it would act equally on the low FIB elements and the high FIB elements. So it wouldn't change the composition anymore. But so the composition change, the plasma composition changes are locked in at transition region level, but then it's also important what kind of transport do we have for this plasma to go into the corona, because the properties of this upwards flow are going to determine how fast changes that happen at transition region level are observed in the corona, where are reflected in the corona where we observe them. And then once we are in the corona, the plasma composition along a certain loop can also change as a consequence of reconnection. So we have two loops that reconnect. If their initial abundance, if initially they have different Fib bias levels, so they have different abundances, after they reconnect, the plasma along these two loops will mix. So we'll end up with two loops that have changed plasma composition that is simply a result of plasma mixing because of reconnection, and it doesn't have anything to do with the Fib effect. And then once we leave the corona and go into the solar wind, we no longer care about the Fib effect won't change the composition anymore, plasma mixing won't change the composition anymore, but then we need to start thinking about other processes like gravitational settling or Coulomb friction as the plasma goes into the solar wind. And these are all things that change plasma composition, but then plasma composition also has an effect on other things like the radiative cooling process of active region loops or flare loops, because radiative cooling in the temperature range between 1 megakelvin to 10 megakelvin is dominated by emission from iron lines. And iron is a low Fib element, so an enhanced Fib bias means a higher iron abundance, which will speed up the radiative cooling process by a non-negligible amount. So this is an example of how plasma composition can affect other things. So yes, as I said, focusing on active regions, which is my main area of interest. On the small scale, we see these variations of plasma composition showing different patterns in the Fib bias showing different values in different parts of the active region, sort of suggesting that different processes that happen in different parts of the active region will influence the Fib bias in different ways. And we see indeed that the Fib bias values within an active region do show quite a large spread. If we look at the distribution of Fib bias in an active region, they all show this relatively wide spread, and they show a right-hand skewness as well. If we look at sort of larger scales and take the active region as a whole and track it over time, we see that the Fib bias of the active region as a whole changes with its evolutionary stage. So in the emergence phase, when the flux first, this magnetic flux first emerges in the corona, it shows signs of photospheric composition, which makes sense because this plasma is emerging from below the photosphere, so it will not have time to for the fractionation process to happen. But once the loops are established and we start getting more wave activity, then the Fib bias starts to increase as a function of time throughout the emergence phase of active regions. And then once the active region starts going into its decay phase, then things like plasma mixing become more important. Plasma mixing between the active region and its surroundings become more important for the Fib bias of the active region. So as the active region reconnects more with the surroundings, the Fib bias will go down until eventually it starts reaching quiet sun values and sort of disappears into the quiet sun towards the end of the active region's life. So the first study I'm talking about today is this large scale variation study. So we looked into 3 of these full sun Hinode ice scans, and we took all the active regions there, and we tried to figure out if there is a link between the Fib bias observed in the active region and other active region properties like magnetic flux or age or evolutionary stage and so on. And the main correlation that we found is the correlation with active region evolutionary stage. So we divided the active regions into a few categories depending on not on their age, but on their evolutionary stage. So active regions that are larger will have a longer lifetime. And we didn't see a correlation between the Fib bias and the age in terms of number of hours or days. But we can also, if we sort of normalize the age by the total lifetime of the active region, that should give us the evolutionary stage. We can't really do that. We can't sort of actually calculate the, I don't know, that the active region is at 50% of its lifetime or 70% of its lifetime. But we sort of put the active regions into some main categories that follow an active region's evolutionary stage. So the first category is an emerging active regions, with and in this category, the median Fib bias is about 1.7, which is a relatively low. Then we have active regions that have sunspots. So the active regions that still have sunspots are sort of at the peak of their activity, and they show the highest median Fib bias. And then we have three categories of progressively more and more decayed active regions, which show progressively lower Fib bias values. So this is sort of in line with what I was saying before, that in the emergence phase, the Fib bias is increasing, but then is decreasing in the decay phase. And the properties of the distributions within these active regions seem to vary with the evolutionary stage as well. And I have two examples here showing the distribution of Fib bias values in an active region that's early in its evolution, in an early evolutionary stage, and one in the late evolutionary stage. And the one that's in the later evolutionary stage has a lower median Fib bias, but it also has a larger standard deviation and a stronger right-hand skewness. So this is likely indicative of the fact that as active regions, when active regions reach an advanced decay stage, you have, first of all, they take up a larger area of the sun. So you have more processes dominating different parts of the active region, which is going to change the Fib bias in different ways. So that's why we get this larger spread of Fib bias values. And we also looked into, we found a correlation between the Fib bias and the magnetic flux density. So this plot is showing the Fib bias as a function of magnetic flux density. And there are two parts in this plot. There seem to be two sort of populations in this plot. So below about 200 Gauss, we see a potential increase of the Fib bias with magnetic flux density. And one potential explanation that we found for this is that in this sort of, I'm going to call it the low magnetic flux density regime, if we increase the magnetic flux density, then we get stronger heating at the chromospheric foot point, which is going to create stronger ionization of the low Fib elements there, and it will lead to a higher Fib bias. But this doesn't seem to continue past about 200 Gauss. So in this region, the plot seems to flatten out. And in this region, we also see that all the data points have sunspots. So there must be something about sunspots that's making this stop. And the potential explanation on this side is that if we increase the magnetic flux density past a certain point, then convection starts to be inhibited, which means that the temperature at chromospheric high will decrease, which will lead to weaker ionization of the low Fib elements, and therefore lowering the Fib bias values. And it's actually not, this is sort of validated by an example. I have an example here of looking at the plasma composition of a very large sunspot, and the contours I'm showing on the Fib bias map are, the first one is the umbra, and the second one is the penumbra. And in the sunspot umbra, even though the magnetic flux density is really strong, and this is part of an active region, obviously, the sunspot umbra shows values almost close to photospheric. So there must be something about this really high magnetic flux density that's making the Fib bias or the Fib effect stop, essentially. And what's interesting about this plot as well is that it is an indirect link between the Fib bias and the magnetic and the evolutionary stage of an active region, because as an active region ages, it will go from having from having sunspots and a higher magnetic flux density to having sunspots dispersing and magnetic flux density going down. So essentially, an active region would go from the right-hand side to the left-hand side on this plot throughout its lifetime, with its, and the Fib bias is going down as well, which is what's happening in this plot too. And another interesting aspect was in some of the active regions we looked at in the study, we saw an asymmetry between the Fib bias values measuring the leading and the following polarities of the active regions. And we seem to see this asymmetry in regions that have different magnetic flux densities in the leading and the following polarities. This is it's sort of known that active region polarities evolve asymmetrically throughout an active region's lifetime. So the leading polarity tends to form a sunspot, a complex sunspot that remains compact for a longer period of time, whereas the following polarity doesn't become as compact or becomes more dispersed more quickly. So what essentially that means is that we end up with the leading polarity having a higher flux density than the following polarity. And we also found that the leading polarity has a lower Fib bias than the following polarity. So it is probably this difference in magnetic flux density that also leads to the imbalance in the Fib bias values that we see. So this was sort of at larger scale structures, but in the second part of what I want to talk about today, I looked at sort of smaller scale structures within an active region. And the target we chose is this active region that is part of an activity nest. So what that means is that we have repeated flux emergence happening in the same area. So that means we have flux emergence in a region of pre-existing strong or complicated magnetic environment. In this case, this active region lived on for many months, but we're capturing it right after a new episode of flux emergence. And this new episode of flux emergence divided the active region into two main parts. The new loops, I'm going to call them the new loops and the pre-existing loops. So the new loops are these brighter, smaller, hotter active region loops that make up the core of the active region. And they're also younger because they're formed by the flux emergence. And the pre-existing loops, which are older loops that had formed before the flux emergence happened. So these are older loops, they're fainter, and they're less hot than the active region core. And what we wanted to look at in this study is, one, if we have loops with such different properties and histories, are they going to show different Fib bias values or plasma composition patterns? And are they going to evolve differently over time? So we tracked them for over 13 hours to see how they evolve.
That's a good question.
Yeah.
About that. How do you know for sure you have the same loop and it's new? You're looking at a certain temperature range. So if I have a loop that's heating or cooling, not necessarily disappearing or forming temperature change.
You mean from one scan to
You're
the
looking at
next?
AIA 193.
Yes.
So I'm just thinking, it's not so clear cut to me how you track, okay, that's a new loop and that's pre-existing loop.
We're kind of we're not looking at individual loops, we're sort of looking at the loop population, and we're trying to get the Fib bias of the, the active region core as a whole, or these pre-existing loops in the south. We're kind of assuming the Fib bias is going to be the same in the pre-existing loops and the new loops, kind of as a population rather than trying to identify an individual loop. Does that mean?
Okay. I'm still not sure how, I'm not sure I could do that. But okay, so why don't you keep going and I'll just think about it more.
Okay.
I just know you're looking at a given temperature range. Things can change in temperature. Let's keep going and just.
Okay. Okay. Yes. So we looked at measuring the fit bias in those two sets of loops, and we used two different diagnostics for this, the silicon-10, sulfur-10, and the calcium-14, argon-14. So there are two main differences between these diagnostics. The first one is the difference in the ionization potential between the elements involved in the diagnostic. So silicon and sulfur are relatively close to each other, but calcium and argon are further away. And the second, and this is the difference that I'm going to explore further. The second difference is the lines form at slightly different temperatures. So the silicon-10, sulfur-10 forms at about 1.5 megakelvin, calcium and argon form at about 4 megakelvin. The loops we're looking at emit at both these temperatures, and we're not exploring this link with the temperature further, but it's just something to keep in mind that is also different between the two diagnostics. And just before showing the results, I'll just quickly describe the fit bias measurement methods that we're using. So the intensity of the spectral lines or any spectral line, the intensity is proportional to the abundance of the element producing the line, and also proportional to this term on the right, which is the contribution function times the differential emission measure. So the contribution function is showing the temperature response of a given line, and the DEM is showing the distribution, the plasma distribution as a function of temperature along the line of sight that we're observing. So if we really arrange those two equations at the top, we can get the fit bias is proportional to the spectral to the ratio between the spectral lines involved in the diagnostic, but it is also proportional to this term on the right, which is essentially telling us how the spectral lines we are using respond to the temperature structure of the plasma we're observing. So ideally, if the two lines that we selected have the same contribution functions, this term will be 1, but that is never the case. We can get close to 1, but it's never going to be 1. So we're using two methods in this work. The first one is the line ratio method, which is just taking this part, the ratio between the two lines involved in the diagnostic, and assuming the second term is 1. This is really easy to calculate, obviously, but it does mean we cannot confidently say all the changes we're observing are only due to temperature, to composition variations. They could also be due to temperature or density variations. The second method is to actually compute the differential emission measure, and calculate the term on the right, which removes the sensitivity to temperature and density, but it is computationally expensive. So we only did it in a few key locations. So these are the results that we are getting. And so the top row is the first scan, the second row is the second scan. I'm showing silicon-10 intensity, and then the silicon to sulfur line ratio, which is the proxy for the fit bias, but it's still sensitive to temperature and density variations. And then calcium-14 and calcium to argon line ratio. So we calculated the line ratio everywhere in the scan, but then we did a DM analysis in a few key locations that are highlighted with the boxes on these rasters. And when I'm talking about the fit bias values, I'm only referring to the ones in the boxes, but I'm still showing the line ratio as a proxy for what the variation is in other parts of the scan. So in the emerging loops, we have the silicon to sulfur fit bias going from 2.3 to 3, and the calcium to argon going from 2.6 to 3.3. So there is an increase in both, which is reassuring because this part of the active region is in its emergence phase. So we do expect some increase over time, some increase in the fit bias over time. But we also see these slightly higher values in the calcium to argon compared to the silicon to sulfur. And in the pre-existing loops, silicon to sulfur goes from 1.8 to 2, calcium to argon goes from 4.3 to 7.8. And first, that's a big jump, but also the calcium to argon values show consistently a higher value, higher enhancement than the silicon to sulfur. So we ran some simulations with the ponderative force model to try to explain why this could be the case or what could drive this. And these are the results from the ponderative force model simulations. So the top row is just showing the properties of the chromospheric environment. So we have temperature and density as the function of height from the photosphere at 0 all the way into the corona. And then the ionization fraction in panels B and C for low FIP elements in panel B and high FIP elements in panel C. And the reason they're on different panels is because the y-axis is very different. And then the second row is showing the simulation that best matched the results we saw in the emerging loops. And the third row is showing the results, the simulation results that best matched what we observed in the pre-existing loops. So we found the best match with the results in the emerging loops if we have a resonant wave driver. So we were essentially varying the properties of the wave driver and tried to get results that match our observations. So if the wave driver was at resonance with the coronal loop, then we find that the ponderomotive acceleration is strongest at the very top of the chromosphere / the transition region level. And in that case, we see enhancement in calcium and silicon, but no enhancement in sulfur and argon. For the pre-existing loops, the best match was when we drove the fractionation process with a non-resonant driver. And in that case, the ponderomotive force is driven much lower down in the chromosphere. And it's also driven over a larger portion of the chromosphere as well. So this results in a stronger fractionation process, which, yes, enhances calcium and silicon as before, but it also produces some enhancement in sulfur, because if you remember, sulfur was sitting very close to the boundary between the low FIP and the high FIP elements. So if we change the properties of the fractionation process a little bit, sulfur can become enhanced as well. So bringing that back to together with observations, in the emerging loops, we see this enhancement in both silicon and calcium, but no enhancement in sulfur and argon. And this is what we see in the observations and the simulations as well. But both the simulations and the observations are showing slightly higher values for the calcium to argon compared to silicon to sulfur. And this is just because calcium has a slightly higher ionization fraction than silicon, so it will be affected by the fractionation process a little bit more. And in the pre-existing loops, the simulations are showing this enhancement of sulfur as well, which is likely the reason why we see those very different values between the silicon to sulfur and calcium to argon values in the observation. So what's happening is when we take the calcium to argon ratio, this is going to show the full enhancement of calcium. But when we take the silicon to sulfur ratio, because we're using sulfur as the reference and the reference is also shifted up, we're only measuring, we're not measuring the full enhancement of silicon. So just to sum up, if we have resonant waves, we drive the fractionation process at the top of the chromosphere and we see no sulfur enhancement. And if we have non-resonant waves, we drive the fractionation process lower down in the chromosphere and we see some sulfur enhancement. So this means that the chromospheric height of where we drive the fractionation process is going to influence the composition pattern we observe. And that also means that in theory, we could use the composition pattern we observed to work our way back to understanding where the fractionation process is driven in the chromosphere to explain that composition pattern, and then maybe eventually even work out some of the properties of these waves, to be able to characterize them. And I think I should probably, I had 2 more slides, but I think I should probably stop for questions. But yes, I'll leave the conclusions here and I'll take more questions. Thanks for listening.
Any questions?
Thanks. Yes.
No, it's great. Thank you. I think, understand a little bit of positive motive force. So the idea is that there are these waves in the corona that are driving, or are they the waves?
There's a bit of discussion about where the waves are coming from. So the original ponderative force model suggests that the waves are coming from the corona, from nanoflares, for example. There's another study suggesting that actually these waves come from below the photosphere. So yeah, there's a bit of discussion on that.
I mean, it seems like it'd be interesting to compare the wave power in the chromosphere with the where you see the FIP effect in one of these regions, right?
Yeah.
Look at the 3-minute waves, the power distribution, underlying the FIP effect.
Yes, I think the 3-minute waves don't have the right properties to enhance. I can't remember the full explanation. They don't have the right properties to, or the enough power to explain the FIP effect. But I think if there's some mode conversion, or
I mean, it must be the dominant power in the chromosphere is that 3-minute, right? There's nothing at longer periods, and anything at shorter periods, higher frequencies is probably some kind of turbulence or mode conversion in the chromosphere. So
okay.
that's what I would, they may need shorter period waves to drive this, but I expect it would have to somehow, those shorter period waves are probably going to be related somehow.
That was kind of an argument for a coronal origin, because then you would get higher frequencies, higher frequency waves, which seem to be more efficient in driving the fractionation process.
Right. So my other question, so the idea is you have the lower FIP things are more easily ionized, and so they get pushed up into the corona more easily. So you would expect somehow some different behavior in terms of these ionized species moving upwards more easily.
Yes.
And this sort of relates to this fundamental mystery, I think, of the chromosphere, in that there is very little apparent difference between the ionized and the neutral, species in the chromosphere. The neutral hydrogen, the neutral helium seems to extend and behave identically, or even go up higher than what you see from ionized, say, calcium. There are a lot of other effects in terms of abundances and just number density and line formation and so on. But the spicual behavior, right, which somehow must be related to this, I would expect, because I don't know.
Yeah, I don't know. I
don't know.
But yeah, I'm not sure how spicules are linked to the FIP effect. Maybe that's something to look into.
Right. But again, that's another dominant behavior in the chromosphere. And to say, well, this is something that's invisible, that's going on. I mean, it could be, but, trying to connect this idea that these ionized species are being pushed upward or pulled upward more easily to everything we've seen, that there's not a lot of difference in those behaviors. And they, then there's, a strong ambipolar diffusion effect in there as well. So I don't know. It's just confusing that there's some, in my mind, other people might have a clearer picture, but this idea that there's a strong different process going on there when that's never been apparent in any other diagnostic is.
You mean in the chromosphere? Yeah, in the
chromosphere, right?
Diagnostics. I think one kind of issue with that is with current instrumentation, we can't measure the Fib bias in the chromosphere or like anywhere in the chromosphere. It might, the model suggested in some cases it happens at transition region level. So maybe it happens in that thin layer rather than happening.
But that transition region level is going to be around a spicule. That's where the
Oh, right.
transition, it's not, right? There are going to be all these spicules and the transition region is around
Mm.
this very dynamic driven structure. So I don't know. Yeah.
Yeah, one example that I actually had a slide on is looking at chromospheric signatures of these of the ponderative or the fractionation process. So maybe I'll actually chat about it quickly. So this study used iris data to look into chromospheric signatures, kind of trying to, we're modeling the chromosphere and then we're observing the corona. So we're trying to fill in that gap and observe signatures in the chromosphere of the waves that are supposedly creating the fractionation process. So in this study, I'm going to focus on the orange and the blue squares. So the blue square is focusing on the leading polarity of this active region, and the orange is focusing on the following polarity. And as I mentioned in the previous study, the leading polarity in this active region also has lower Fib bias than the following polarity. And so the study looked at whether there are any differences in the chromospheric observations in the leading versus the following polarity. So the first thing they looked for is the non-thermal line widths of the silicon-4 and carbon-2 lines. And that is what's shown on the bottom plot here. So first for silicon-4, 1394, silicon-4, 1403, and then carbon-2. And in all instances, the following polarity showed a much stronger line width than the leading polarity. So a much stronger line width would suggest stronger signatures of unresolved velocity due to alphane waves. So this would be in line with the ponderative or with this wave scenario. So if we have more waves in the following polarity or stronger waves in the following polarity, that leads to the stronger fractionation. The other thing we could look for is the velocities of different features of the magnesium-2 line. So this work looked at the magnesium-2, K2 and K3. So the K2 is forming lower down in the chromosphere and the K3 higher up in the chromosphere. So in this active region, apart from the fact that the leading polarity had lower Fib bias than the following, the following polarity had higher Fib bias than the leading, but it also showed a higher difference between the silicon to sulfur and calcium to argon, which means, according to the model, that we should see the fractionation process should happen lower down in the chromosphere compared to the leading polarity. So in this work looked at whether the velocities measured by these features in the magnesium line are different in the leading versus the following polarity. And this is what the plot in the middle showed. So sorry, this is a complicated plot. It's it's a plot of all these properties as a function of time. The top is showing the Fib bias. The second one is showing the silicon-4 line width. And again, it is higher as a function of time. It's consistently higher in the following polarity in orange than the leading polarity in blue. And then if we skip to the third panel, this is showing the magnesium-2 K2 velocity. So it's looking at the middle of the chromosphere, and the signatures are not as strong as in the non-thermal velocities or non-thermal line widths, but the leading polarity seems to show higher, again, consistently higher velocities in the mid-chromosphere than the leading polarity. So this would be consistent, and magnesium is a low Fib element, so we would expect to see a stronger speed for magnesium lower down in the chromosphere if that's where the fractionation process is happening. So this could be one way to start looking into this.
If those are line of sight velocities, they're
Yes.
not alphane waves. There must be a alphanic magnetoacoustic, maybe, right? You know, an alphanic wave won't necessarily have a line of sight.
Oh, I'm not talking about the waves anymore. I'm just speaking about the
Okay,
the velocity of the waves are driving this
I see.
ponderomotive force. So what we're seeing is not the waves themselves, but we're seeing the effect of the waves. They're meant to apply this additional acceleration on the magnesium ions in one part versus the other. Yeah. So yeah.
I think Phil has a question.
Yeah, thanks so much for a very interesting presentation. The discussion with Kevin brings up some things for me. Is there an echo on your line?
No.
Pretty clear.
Okay, good. So, what the only thing I would suggest is that neither NASA nor the NSF or anybody has taken the upper chromosphere seriously enough to actually measure the magnetic fields properly. And as a result, you're just guessing. And I got in trouble about 20 years ago at a meeting discussing the upcoming IRIS mission. And the reason I got in trouble was I was saying you're measuring the wrong things. And they were measuring the wrong things because we'd measured those before. Many missions to observe UV intensities. One mission to observe UV polarimetry, and that one was partially successful. It wasn't ideal. That was UVSP. Now, what I'm going to suggest to you is that you pretty much ignore all models and all observations of the upper chromosphere at this point, and you continue with an empirical study of the kind that you're doing, and just develop a really strong observational picture as best you can of these things in the way you've done. I would say that comparison with models is completely premature until you can measure aspects of the magnetic field. The other point is that when you have unresolved motions, you have no idea what the nature of those motions are. So, for instance, this ponderomotive force model is a sort of plane parallel kind of, idealistic model where you represent the observed variations in widths and what have you by a bunch of alphane waves, and you look at the consequences. And that has never been properly tested, in my view, to try and disprove it. And disproving things is what you need to do to make progress in science. And so also things like spicules, there's one fatal problem with spicules that you can never get around, which means that they cannot be very important for the corona. And that is, they are such narrow things, and it's been well documented, already in the low beta plasma. That means the magnetic fields have expanded into 3D space over areas that are about 1,000 times bigger than the spicule itself. And you cannot transport energy or plasma across those spicules to fill the corona. So spicules are a red herring completely. And so this is heresy. I've made lots of enemies as a result of criticizing these things. I'm at the end of my career, but it's not about me. It's about keeping an open mind. And I really encourage you to continue with your empirical research. And I'm very pleased to see the details in which you're going to. Do not trust any calculations of the upper chromosphere. Always be self-critical with your, the possible errors you can make. Things like assuming statistical equilibrium in the corona, for instance, is not a guaranteed thing at all. But just continue with the empirical science. Try and disprove how various models are there instead of trying to find agreement with them. So I'm sorry if I'm lecturing, but I really enjoyed your talk. I think the work you're doing and the approach you're taking is very important, but I think it's really important also to recognize that things like small scale reconnections, as well as things like waves, we have no idea what's going on in the upper chromosphere. We don't even know center to limb variations, for instance, of line width very well, which is tragic at this point. And things like these empirical facts need to be sorted out. But anyway, I really enjoyed the talk, and I look forward to seeing results in the future.
Thanks a lot for the comments. Those are very interesting. I'll keep those in mind. Thank you.
Well, by all means, ask me any questions you like, anytime. I'm full of contrary ideas. And so if you enjoy challenging the way you think about things like the sun, by all means, contact me. Otherwise, you can just plain ignore me, because I'm enjoying an approach to retirement fairly soon. So anyway, thank you so much.
That's very kind. Thank you. And thanks for the comments.
Yep. Any last minute questions or comments? If not, thank you again.
Thanks for listening.